Alright, so before we get into extending the concept of sine law and cosine law a bit further in 3U, we're going to take a bit of take some time to review how sine law, cosine law worked when we first saw it back in grade 10. So first thing you might remember, well, why do we need sine law, cosine law in the first place? Well, it's to solve triangles that are not right. So when we had right triangles, we could use SOHCAHTOA or Pythagorean theorem. None of those work, however, with right triangles. You have to use either sine law, which you might remember is this equation right here, or cosine law, which is this equation right here. So the big thing with sine law is it compares the ratios of corresponding sides. So the side with the angle, the sine of the angle across from it, it's the same ratio for every pair of angles. Note that convention here, you might remember, is that when we label a triangle A, B, C for the angles, sides A, B, and C are across from their respective angles with the same letter. So for example, side A is across from angle A, side B is across from angle B, side C is across from angle C. And you'll see those relationships when you see the equations as well. So in the sine law here, again, if you're trying to set up a ratio, it's the angle and side that are across from each other. They're using each ratio. Okay, similarly in cosine law, when you have, for example, a side by itself on the left side, a squared, it's going to be cosine of a, the angle across from it on the other side of the equation. Okay, so when we have those two equations, remind yourself when to use each, and there were these rules that you saw back in grade 10 that, again, if you had a side and two angles, we use sine law. If we had three sides, no angles, we use cosine law. If we had two sides and the contained angle, remind yourself what contained and uncontained angle mean. So let's say, for example, if I gave you two sides here, let's say this was 12 and this was 20. If I gave you the contained angle, I'd be giving you this one right here. Okay, so if I gave you the contained angle, you'd be using cosine law to solve for the side across from that angle. If I did not give you the contained angle, let's say I gave you, I don't know, either this one or this one, you'd be in a situation where you're using sine law. Now, again, I don't recommend memorizing this table. I mean, you can if it helps you, but the thing to remember here, it might make it a little bit easier to remember when to use sine law, cosine law. If you want to use sine law, you need an angle and a side across from it, so one of those pairs to complete a ratio, and one other piece of information. Okay, so for example, in the case here where we have the contained angle, I have the side of 20, but I don't have the angle across from it. Okay, so I have the side 12, I don't have the angle across from it. I have this angle, but not the side across from it. So I have no angle side pairs, so I can't create a ratio in sine law. I have to use cosine law. However, down here, if I give you this angle, we have an angle side pair right here with that side and that angle, and then I can use that ratio to solve for another angle or another side somewhere else in the triangle. Okay, so if you remember that rule, you'll always know when to use sine law or cosine law. Okay, a couple of definitions to remind yourself of. Angle of elevation, angle of depression. So if you see these terms used in a word problem somewhere, know what they mean. So the angle of elevation is the angle made from a horizontal up to some level, usually a line of sight, to the top of a building or top of a flagpole or something. So this right here would be the angle of elevation. The angle of depression is the angle made from the horizontal down to a certain level. So again, something like that right there. Okay, a couple other ways we saw dealing with directions, a few ways of dealing with it, talking about headings or talking about bearings. Heading, it gives you a direction going north, east, southwest, something along those lines with an angle. Bearings are given in terms of angles rotated clockwise from north. So I'll give you an example of each. Okay, so let's say, for example, I'm giving you a heading of north 80 degrees east. Well, the way you draw that, you start off by going north and then go 80 degrees to the east. So overall, your object, boat, plane, car, whatever, is going northeast, but you go north first and it's 80 degrees to the east of north. So the angle here with the vertical is going to be 80 degrees. Okay, let's say I want to do south 17 degrees west. I'd be going south, but 17 degrees to the west of that, so somewhere down here, where this angle is 17 degrees. Okay, let's say, I'll give you guys another one here. Let's say I want to do west, use a different color here, west 31 degrees north. So first direction here I go is west, and I go 31 degrees north of there. So that would look something like this. Okay. Now, if I give you a bearing, well, a bearing, again, it's the angle clockwise from true north. Okay, so let's say somebody's traveling on a bearing of 42 degrees. Well, from true north, 42 degrees clockwise is somewhere over here, so it's going off in this direction. Okay, let's try another one. Let's say I give you a bearing of 191 degrees. 191 degrees clockwise from true north puts you somewhere down here in this quadrant. So 180 gets you here. An extra 11 degrees would get me to 191. So this would be a bearing of 191 degrees. Okay, so if you see these mentioned in word problems, that's what they mean. Okay, you can see a few more examples of these down here. So let's say we have a plane flying on a bearing of 70 degrees. So that's this first arrow right here. So it's 70 degrees clockwise from north. It takes you this direction. And then from there we go on a bearing of 45 degrees. So again, true north from there, 45 degrees clockwise means you're going this direction. If you want to represent that exact same situation using headings, well, we'd say they're going north and then 70 degrees to the east. And then from there going north 45 degrees to the east. So just two different ways of representing the exact same course that an object might be taking, but again, just know what they mean so you can set up a word problem appropriately. Okay, now we've looked at all those definitions. Let's do some examples. So I'm going to want you to try these ones on your own first. See what you remember using grade 10. So first of all, figure out what you can inside the triangle. Try and decide whether or not you can use sine law or whether or not you have to use cosine law, and try and solve for the missing value in both A and B, and push play and ready to go through the answers together. Alright, so we can take a look at the answer for the first one here. I got 34.6. Now, just to recap how I did that, first off I saw I had two of the three angles in a triangle, so since all the angles in a triangle add to 180, I got 79 degrees for my third angle. Once I did that, I had a side angle pair, so I knew angle 79 degrees and the side across from it, so I can build a ratio to that, sine 79 degrees over 87. That'll be equal for every other pair of corresponding sides and angles in the triangle. So if I want to solve for x over here, I use the 23 degrees across from there. So sine 79 degrees over 87 equals sine 23 degrees over x. And then it's just a matter of using algebra to solve for x. So I multiplied the x, both sides by x, moved over to the left side of the equation. I also multiplied both sides of the equation by 87 to move that out of the denominator over to the right side of the equation. So I wound up with, in one step there, getting x sine 79 equals 87 sine 23. Divided both sides of the equation by the sine of 79 degrees to get my next line down here. So I have x isolated. I just need to run all this through my calculator. I should get about 34.6 for an answer. Okay, down here in B, you should have gotten 103.8 degrees. In this situation, I have three sides and no angles, so I don't have any angle side pairs. I have to use cosine law. So I can use cosine law to solve for any angle I want. I'm going to choose to solve for, well, the one I'm looking for, save myself some time. So if I'm solving for theta, I have theta in the equation over here. In the cosine law, the side that's by itself in the equation on the left side has to be the one across from that angle. So it's going to be side with length 18. The other two side lengths, 7 and 15, fill in the other two spots in the equation for sides. So I have 18 squared equals 7 squared plus 15 squared minus 2 times 7 times 15 times the cosine of theta. And from here on in, it's just algebra. Now, the algebra can be a little bit tricky. Just be very, very careful. It's easy to make a mistake. So what I did here is I squared everything here. I multiplied these. And then here at this point, I did 324. I subtracted 49 from both sides of the equation. And I subtracted 225 from both sides of the equation to get 50 on the left side. Now, the really common mistake that a lot of people do in this step is they go 49 plus 225 minus 210 and say that's, and then combine them all into one term. You can't do that because of BEDMAS here. You have multiplication happening here between the 210 and the cos theta, so it's not a like term. You can't combine it with the 49 and 225. So that's why I move the 49 and the 225 to the left side of the equation first. When we get down to this step, we divide both sides of the equation by negative 210. Okay, which reduces to negative 5 over 21. That gives me cos theta. And then remember, if I'm trying to solve for theta, I take the cosine inverse of each side of the equation to get 103.8 degrees. Okay, so a couple of examples there of the kind of things that you would have done back in grade 10. Okay, here's a couple more I'd like you to try. Just start by setting up C and see what happens. Okay, so on the surface this looks very, very straightforward. I got a side angle pair here. So I have the sine of 30 degrees over 5. And I'm looking for theta, so I have another side angle pair here. So it's going to give me sine theta over 8.3. Okay, so I'm going to multiply both sides of the equation by 8.3. So I get 8.3 times the sine of 30 degrees all over 5. And that's going to give me sine theta. So if I want to get theta, remember, it's going to be the sine inverse of that entire thing. Okay, so write that out again. Okay, run that through your calculator and see what you get. Okay, when I run through my calculator, I get theta being 56.1 degrees. However, does that answer make sense if you look at the diagram? And hopefully it doesn't, because if you look at the diagram the way it's drawn, theta is actually an obtuse angle. Okay, and this presents a particular problem here because it means our calculator didn't give us the right answer. The actual right answer here is going to be 123.6. Okay, and that should actually be 0.9, not 0.6. So the reason being, what presents a problem here is because if you think about our cast rule, if you look at an angle that's from 0 to 90 degrees, so an acute angle, or an obtuse angle, one that's between 90 and 180, the sine ratio is positive in both of these cases. So even though we can see from the triangle that our answer should be acute, our calculator is spitting out the possible answer in quadrant 1. It's not an issue using cosine law because it's not the same sign in quadrants 1 and 2. The sine ratio is the same sign, positive in both quadrants 1 and quadrant 2. So in this situation, you have to recognize here that even though your calculator is giving you 56.1 as an answer, your answer should actually be the answer in quadrant 2, which should be 180 degrees minus the answer your calculator gives you. Okay, so that should give you 123.9. So you have to be very, very careful now. We can't necessarily just blindly accept every answer a calculator gives us. We have to make sure it makes sense given the diagram. So in this case, again, theta is clearly obtuse. So the angle that our calculator is giving us is wrong, so it has to be adjusted for. We have to find the answer in quadrant 2, not in quadrant 1. Okay, so with that business behind us, let's go back and try something a little bit easier. From grade 10, you have a right triangle here. Try and solve for the missing angle. So take a minute, try that on your own, and push play and you're ready to see the answer. Alright, so with SOHCAHTOA, first thing I want to do once I choose the angle I want to work with or solve for, in this case this one, I label my sides accordingly. So my longest side is the hypotenuse, the side across the triangle from my chosen angle is the opposite, the last one's the adjacent. So I have the adjacent and the hypotenuse. I want to solve for the angle, so the ratio I'm going to choose is the cosine ratio. So cos of theta will be 16 over 18. I take the cos inverse of both sides, and I get 27.3 degrees as my final answer. Okay, so with E, the first thing I just want you to do is solve for x. I know it says, for example, to solve the triangle above, just start by solving for x. And again, figure out which rule you want to use, try and figure it out, and we'll run through it together when you're ready. Okay, so you'll notice here that we have two sides given in the contained angle. So I have no side angle pairs completely known. I have to use cosine law, and I can use cosine law in this case to solve for the side opposite the known angle. So I have cosine 22 in the equation, which means the side across from that x is x squared over here. I put in my 15 and 20 for the other two sides in the equation. Run that through my calculator, solve. I should get x being approximately 8.3 units in this case. So example 2 would like you to solve the entire triangle, which means find all the missing sides and angles, all missing values. So we now have all three sides, just the two angles left to find. I'm going to let you try that on your own, and we'll run through this in part 2. Okay, we'll see you over there.